Hello everyone, welcome to our channel. This is Dinesh MA, working as Assistant Professor in the Department of Electronics and Communication Engineering, Maharaja Institute of Technology, Mysore. In the next series of videos, we will understand the concepts of bipolar junction transistor. And the scope of this series is limited to these topics. We will be understanding or discussing the current equations associated with a BJT and how a BJT will be working as an amplifier, both as a current amplifier and BJT amplifier we'll understand, and different configurations, what are the different configurations associated with a BJT, and the common emitter characteristics, common base characteristics and common collector characteristics of a BJT, and then what is DC load line with respect to a transistor and how to construct the DC load line for a transistor. So these are the concepts what we'll be discussing in the following series of videos. So before getting into these topics, we'll brush up the fundamentals of bipolar junction transistor. Let us understand some of the basic concepts associated with a BJT. The full form of BJT is bipolar junction transistor. And we have two types of BJTs. One is NPN, another one is PNP BJT. And the structure of the BJTs are shown in these figures. This is how a PNP transistor looks like, and this is how an NPN transistor looks like. And the symbols of NPN and PNP transistors are shown in these diagrams. As I mentioned, the BJTs will be having three terminals: emitter, base and collector. And in the structure and the symbols as well, we can see the three terminals: emitter, base, collector, emitter, base, collector. And this is same even with the NPN transistor. Let us understand the operation of the BJT considering NPN transistor as the reference. So before getting into the operation, if we look at the structure of the BJT, we have emitter region which is made up of N type, and base region which is made up of P type, and collector region which is made up of N type in an NPN transistor. Whereas in a PNP transistor, the emitter region and collector regions are made up of P type. In between we will be having an N type base region. Now let us understand the operation of the NPN type of BJT. Now to understand the operation of this, we need to bias the transistor just like we bias the semiconductor diode. So let us bias the transistor, and here the emitter base region will form the input circuit and collector and base region will form the output circuit. To understand the operation, we need to forward bias the input circuit. So here you can see the emitter is N type, so we shall have negative polarity connected, negative polarity of the battery connected to the emitter region, and the positive terminal of the battery should be connected to the P type base region. And on the output side, the N type collector should be connected to positive terminal of the battery, whereas the P type base should be connected to negative terminal of the battery. Now when we have done so, the electrons which are the majority charge carriers that are available in the N type emitter region will move towards the base region, and base, we can see here the thickness of the base is less because the doping done here is light. So here some of the electrons which comes from the n-type emitter will recombine in the base region, p-type base region, and there will be a small amount of current that will be flowing into the base terminal, and the remaining electrons will be moved and collected at the collector region, and maximum current will be flowing in the collector terminal. So we can say here IE, which is emitter current, is equal to the summation of base current and the collector current. IE is the emitter current, IB is the base current, and IC is the collector current. Let us indicate these things in the symbols also. So here this is the emitter current IE, and this is collector current IC, and this is base current IB. And the voltage between the base and emitter will be represented as VBE, and the voltage between collector and emitter will be called as VCE, and the voltage between base and collector will be called as VBC. So these are the voltages and currents associated with an NPN transistor. Now let us understand the current gain factors associated with the BJT. Now let us understand the current gain factors and the current equations associated with any BJT. Considering an NPN BJT or a PNP BJT, we'll be having two current gain factors. Number one is emitter to collector current gain, emitter to collector current gain, and this is represented as alpha DC, and the second current gain is called as base to collector current gain. Second one is base to collector current gain, and this is represented as beta DC. And let us understand what these two current gain factors indicates. The first one, the alpha DC or the emitter to collector current gain, is defined as the ratio of DC collector current to the DC emitter current. So this alpha DC can be written as IC by IE. So significantly, this indicates what amount of emitter current is available at the collector layer as the collector current. Whereas the beta DC is defined as the ratio of DC collector current to the DC base current. So this can be written as IC by IB. So this indicates what amount of base current is flowing in the collector terminal or collector region as the collector current. So this is beta DC, that is base to collector current gain. And these two have got the typical values. The typical value of alpha DC is 0.96 to 0.995, and the typical value of the beta DC is 25 to 300. So these two are the current gain factors that are associated with any BJT. Let us understand the relationship between the currents associated with the BJT. Now let us understand the relationship between alpha DC and the beta DC. We know just now we have defined the definition for alpha DC and beta DC. So alpha DC can be written as IC by IE, correct? So alpha DC, which is the ratio of collector current to the emitter current. So IC can be written as alpha DC into IE. But IE, we have the basic definition, which is equal to IB plus IC. Let us substitute this in this equation for IE. So IC is equal to alpha DC into IB plus IC. So this can also be written as alpha DC into IB plus alpha DC into IC. So transferring this alpha DC into IC towards this end, we can write this as IC minus alpha DC IC is equal to alpha DC into IB, and this can be written as IC into 1 minus alpha DC equals to alpha DC into IB, and IC is equal to alpha DC by 1 minus alpha DC into IB. So IC can also be written as alpha DC by 1 minus alpha DC into IB, and if I transfer this IB towards this end to the denominator, this can be written as IC by IB is equal to alpha DC divided by 1 minus alpha DC. But we have beta DC equals to IC by IB. So substituting this here in this equation, we have beta DC equals to alpha DC divided by 1 minus alpha DC. So beta DC can be represented as alpha DC divided by 1 minus alpha DC. So this is a relation between beta DC and alpha DC. Now let us understand how we can represent alpha DC in terms of beta DC. Let us consider this equation, beta DC is equal to alpha DC by 1 minus alpha DC. So let us rewrite that. Beta DC equals to alpha DC by 1 minus alpha DC. So let us cross multiply this. Beta DC into 1 minus alpha DC equals to alpha DC, and multiply this with this term. So beta DC minus beta DC alpha DC is equal to alpha DC, and beta DC is equal to, let us transfer this minus beta DC alpha DC into other side. So this is going to be alpha DC plus beta DC into alpha DC. So beta DC is equal to, here taking alpha DC as common, alpha DC into 1 plus beta DC, and let us transfer this to this end. So alpha DC can be written as beta DC divided by 1 plus beta DC. So here we have the equation for alpha DC in terms of beta DC. So in this equation we have represented beta DC in terms of alpha DC, and here we have represented alpha DC in terms of beta DC. So this is all about the current relationship or the current equations associated with any BJT. We'll understand how a BJT can be used as an amplifier. or how BJT can work as an amplifying device to amplify the voltage and current. First, let us consider BJT as an current amplifier. We know that the beta DC, which is a current gain factor, is given by IC by IB. So, let us say beta DC is equal to IC by IB, and from this IC can be written as beta DC into IB. Here IC is the output current and IB is the input current. Let us say there is a change in the input current IB. So here IC is equal to beta DC into delta IB, whereas delta IB indicates a small change in the input current IB. Because there is a small change on the input current IB and we have the beta DC, which is the current gain factor, the corresponding change will also be reflecting on the output current IC. So IC can be written as delta IC. Now beta DC can be written as delta IC divided by delta IB. So whenever there is a change in the input current delta IB, there will be a corresponding change in delta IC. So this is equal to beta DC. So with this we can understand that BJT can be used as a current amplifying device, right? So now let us understand how a BJT can be used as voltage amplification device, or let us understand BJT as an voltage amplifier. To understand this, let us consider a circuit diagram and the corresponding output characteristics of this circuit. So let me consider a transistor an NPN transistor which is connected in common emitter configuration, and here let us say this has got a biasing voltage VB which is equal to 0.7 volt. So we know any silicon diode which requires at least 0.7 volts to conduct. Likewise, an NPN transistor which is made up of silicon also needs at least 0.7 volts in order to make it on. So let us consider a VB of 0.7 volts, using which we can forward bias the input junction, and let us connect this emitter to the common terminal and say this transistor has got a beta DC value of 50, and here let us connect an input signal Vi, and let us consider the value of this Vi input signal as plus or minus 20 millivolts. Let us consider the value as 20 millivolts, and let us say there is a resistance connected to the collector terminal, and consider the value of this resistance as 12 kilo ohms. Let us call this as R1, and the value of this is 12 kilo ohms, and because of this there is a drop across this which is called as R1 into IC, whereas IC is the current, the collector current that is flowing through the transistor. So let us indicate the collector current IC that is flowing through the resistor element, and the output circuit need to be biased. So let us consider a supply voltage and name this as VCC, and let us say this VCC is equal to 20 volts. Right, so this is a circuit diagram what we are considering, and let us also consider the characteristics of this. Let us draw the input characteristics of this transistor circuit, that is how the input current IB. So here let us say this is IB, the input current IB varies with respect to the input voltage applied. So let us say this is V, this is IB in microamperes, and this is VB in volts. So the input characteristics will be almost similar to the VI characteristics of a diode. So let us say like the scale is in steps of 0.1 volts. Let me draw this. Let me extend this. .8, so this is VB, which is represented in volts. In the same way, let us consider the y-axis, which is IB, in steps of 5 microamperes, 5, 10, 15, 20 and 25. So now let us use the Kirchhoff laws and find out what are the values we'll be having, and let us plot the graph for this. Now consider this characteristics what we have, the characteristics, input characteristics for this circuit. So here we have IB in microamperes, here we have VB in volts, and VB according to the circuit, VB applied is 0.7 volts. So at VB is equal to 0.7 volts, the current what we have, IB what we have is 20 microamperes. Let us consider the equations to find out the value of VC. So first we need to find out IC, and using this we will find out what is the IC, right. So now IC is given by beta DC into IB. And for the given signal VB of 0.7 volts, we have IB of 20 microamperes, and beta DC is represented or given as 50. So IC is going to be 50 into 20 microamperes. So IC is going to be 1 milliamperes. So let us say IC is 1 milliamperes. So with the IC value known, let us apply the KVL for this part to find out what is the value of VC. Now by applying KVL, we can write this VC is equal to the supply VCC minus the drop across this resistance, that is R1 into IC. So let us say VCC minus IC into R1. So we have VCC is equal to 20 volts minus IC is calculated as 1 milliamperes into R1 is given as 12 kilo ohms. So R1 is given as 12 kilo ohms and IC is calculated as 1 milliampere. So with this, VC can be calculated as 8 volts. So we have VC which is calculated as 8 volts. Now to understand how BJT is going to work as voltage amplifier, what we'll do is we'll consider this VI which is varying with 20 millivolts. So let us consider here at this is VB what we have. So this VB will be changed by, altered by plus or minus 20 millivolts. So let us consider here this value as VB minus 20 millivolts and this point as VB plus 20 millivolts, right? So now look at the graph, the corresponding changes what we have on the base current IB. Now if we change this VB by minus 20 millivolts, so we have IB of 15 microamperes. So this I can write as delta IB or minus IB. So what we have on the characteristics, so on that we have a change minus delta IB, that is minus 15 microamperes. Whereas when we change the input or the input VB is altered by plus 20 millivolts, so the corresponding change what we have is 25. So this is the change we have. I can put this as plus delta VB which is plus 5 microamperes, or this is 25 microamperes. This is not 15 microamperes, this is minus 15 this is not minus 15 microamperes, this is 15 microamperes which is minus 5 reduced by the base current reduced by minus 5 microamperes. Now let us understand what is the change that this minus 20 millivolts or plus 20 millivolts on the input voltage VB is causing on the input current IB. In turn, how this change will make a change on the output voltage. Now let us come back to this particular equation. Delta IC is equal to beta into delta IB. So using this, let us substitute the change in the input current IB, right? So with this I can write delta IC is equal to beta DC, which remains same, beta DC 50 into delta IB. Now what is delta IB? We have delta IB is plus or minus 5 microamperes. So I can put this as 50 into plus or minus 5 microamperes. So this data is read from the given data, right? So this will cause plus or minus 250 microamperes. This will cause plus or minus 250 microamperes or plus or minus 2.5 milliamperes. And VC we have the equation here. We can note this: VC is equal to VCC minus IC into R1, and VC can also be written as IC into R1 because VCC is constant. What I am trying to write here is what is the change in the output voltage because of the change in the output current IC. Because the IC has changed by 250 microamperes, plus or minus 250 microamperes. So this delta Vc can be written as plus or minus 250 micro into the R1 value given is 12 kilo ohms. So this will give us a value of delta Vc is equal to plus or minus 3 volts. So now, because there is a change in the input voltage by plus or minus 20 millivolts, this has caused a change in the input current IB by plus or minus 5 microamperes. This change in plus or minus 5 microamperes in the input current has caused a change on the output current IC by plus or minus 250 microamperes, and this change in turn has caused a change on the output voltage by plus or minus 3 volts. So before considering the change on the input voltage, so we had Vc is equal to 8 volts. Now if we change the input voltage, we have a change of plus or minus 3 volts. So if we change the input voltage by 20 millivolts, there will be an output of collector voltage equal to 11 volts. If we change the input voltage by minus 20 millivolts, then the output voltage Vc is going to be 5 millivolts. So from this we can understand that the transistor can also be used in voltage amplification. So in this session we have understood how a BJT can be used in current amplification and voltage amplification. In the next session, we will understand the various configurations in which a BJT can work. Thank you.